Hello again, we're ready for Section 2 of Chapter 13. In Section 2, we're primarily going to discuss recursive definitions, as opposed to explicit definitions, which we talked about in Section 1, although we never actually used that terminology. I've given you here an arithmetic sequence of terms. It goes from 3 to 7 to 11 to 15 to 19. So you can easily tell that the difference between each term is 4. Now, initially, the first term is 3. The first term is 3. A recursion equation for this sequence would go as follows. It'd be the nth term is always equal to the previous term. So it's not the nth term, it's the n minus 1 term. Plus, in this case, the difference, which is 4. So that's how a recursion equation works. The nth term is the term that you are looking for. And to find it, you need to know the previous term. And then you just add to it the common difference, which is obvious from just looking at part of the sequence. So it'd be pretty easy to find T6, T7, and T8 in this case. I've given you 5, 4, 3, 2, and 1. You just add 4 each time. Check this out. T6 would be the previous term, which is T6 minus 1 plus 4, which is really just T5 plus 4. In this case, T5 was 19 plus 4. Answer, 23. What about if you were to find T7? Well, you would take the previous term, which is T7 minus 1 plus 4. Same thing as saying T6 plus 4. And T6 plus 4, that'd be 23 plus 4. Answer, 27. We're just adding 4 each time. What about T8? Well, find T8 minus 1 plus 4. 8 minus 1 would be T7 plus 4. T7 you just found is 27 plus 4. 31. And there it is. That's how a recursion definition works. It's always based off the previous term. But before you can ever get started, you have to have an initial condition. You have to know where the sequence starts. So here's the definition written out. The recursion definition requires 2 parts. It requires an initial condition that tells us where the sequence starts. In other words, T1. We have to know T1. And then it gives you an equation, a formula, that tells you how each term, Tn, is related to the previous term. P-R-E-V-I-O-S. Previous term. In this case, Tn minus 1. Previous term. So, this is how it works. You need T1. In this example, T1 will be 3. And the formula is Tn equal Tn minus 1 plus 4. So the first term is 3, and the formula is you simply add 4 each time. Now, that was, what we use in the example at the beginning of the video. Now, if you'd wanted to write an explicit definition, then you would use the formula from Section 1, the old formula. Tn equals the first term plus n minus 1 times d. Hopefully that looks familiar. In this case, the first term is 3 plus n minus 1 times the difference of 4. Distribute the 4, combine like terms, you get 4n minus 1. That is your explicit definition. Just that formula right there. The nice thing about using the explicit definition is you don't have to know the initial condition. Whereas this 2-part formula is the recursive definition. Sometimes he comes in handy as well. You're going to primarily focus on recursive definitions in this section. Okay, so here are your directions. You are going to find the second, the third, and the fourth terms of each sequence and state whether it's arithmetic, geometric, or neither, and then also find T sub 10. Wow. A lot going on here. So, you know the initial condition. The first term is 2. So let's find T2. T2. Well, in this case, that'd be 3 times Tn minus 1, or in our case, T2 minus 1. Well, that's just 3 times T1. Well, wait a minute. T1 is just 2. It's 6. The second term in our formula is 6. Okay. Let's find T3. Well, that would be 3 times T3 minus 1, or the previous term, 3 times T2. We just found T2. 3 times 6, 18. Pretty easy? Good. What about T4? That would be 3 times T4 minus 1. In other words, 3 times T3. Well, that's 3 times 18. Answer, 54. So, T1 was 2, T2 was 6, T3 was 18, T4 was 54. Hopefully you can tell that that is a geometric sequence where R is 3. We're multiplying by 3 each time. Now I want you to go ahead and find an explicit definition for that sequence. Since it's geometric, we have a generic go-to formula. You take the first term times R to the n minus 1 power. Hopefully you have that memorized now. The first term I gave to you up here is 2. The ratio we just found, 3 to the n minus 1 power. Well, that's just... Well, what you can do with that is the split approach. The split approach. So why don't you go ahead and do that? That's really 2 times 3 to the n times 3 to the negative 1. Notice we just split this up to 3 to the n times 3 to the negative 1. They were side by side, and we split them up. Well, that's really 1/3 right here. This is really 1/3. So 2 times 1/3, 2/3 times 3 to the n power. That's your explicit definition for T sub n, as opposed to the recursive definition, which I was given to you. Then the last part of the directions were to find T10, I think, right? Yeah, up here. So T10 would be 2/3 times 3 to the 10th power. 2/3 times 3 to the 10th power. That would be... You can think of that as 2 times 3 to the 10th power over 3. Well, that's just 2 times 3 to the 9th power. Get out your calculators, and you will get 39,266. That's what the 10th term would be, whether you're using the recursive definition or the explicit definition. Okay, in part B, the initial condition is the first term is 3, and here's your recursion equation. I want you to find T2. Be 2 times T2 minus 1 plus 1, 2 times T1 plus 1, 2 times 3 plus 1, 7. That's the second term. T3, 2 times T3 minus 1 plus 1, 2 times T2 plus 1, 2 times 7 plus 1. 2 times 7 is 14, plus 1, 15. And T4. 2 times T4 minus 1, plus 1. 2 times T3, plus 1. 2 times 15, plus 1. And that answer is 31. Alright, sweet. So let's see if we can come up with a formula here. List all your terms. 3 7, 15, 31. This was t sub 1, this was t sub 2, this was t sub 3, and this was t sub 4. Here n is 1, n is 2, n is 3, n is 4. Each time I'm trying to come up with these formulas, when it's neither arithmetic nor geometric, I always write out my n's. I always write out my n's to help me maybe identify a pattern. So it's not arithmetic because we're not adding the same amount each time, and it's certainly not geometric because we're not multiplying by the same amount each time. So what are we doing each time? To get from 3 to 7, you add 4. And to get from 7 to 15, then you add 8. And to get from 15 to 31, you add 16. Now, hopefully you recognize these as powers of 2. These are the nifty little tricks that you're going to have to pull out of your sleeve when you're dealing with these undifferentiated sequences, the ones that don't necessarily have a direct arithmetic or geometric pattern. So, what I notice here is if this is my list of n's, each time I'm adding, to get from the first term to the second term, I'm adding 1 higher than what n is. Now maybe you see a different pattern, and yours may work. So check this out. So t to the n is really 2 to some power of n, in which case it's n plus 1. Let's see if that's good enough. So let's just check one. Let's try t to the 3, or t3. That'd be 2 to the 3 plus 1 power, which is 2 to the 4th power, which is 16. Oh, wait a minute, our t3 is 15. And how do I get from 16 to 15? I subtract 1. So maybe we should have put a big fat minus 1 here at the end. Let's check it again. Let's try t to the 4th. T4, 2 to the 4th plus 1 minus 1 is really 32 minus 1. And you know what? That's 31, which is what our last term is. Sweet. So I'm guessing that this is our explicit definition for Tn. I'm guessing that that's our explicit definition for Tn. Those are tricky, guys. There's no one easy way to do them. You just have to roll up your sleeves, look for patterns, try to find an explicit definition that works. Okay, find T3 and T4 only in this case. So here's your initial conditions. T1 is 2 and T2 is 4. I was nice to you. And Tn, the nth term, is always equal to the previous term times the term before that. Alright, here we go. It said to find T3 only. That would be equal to T sub 3 minus 1 times T sub 3 minus 2. In other words, it's T sub 2 times T sub 1. Well, T sub 2, you know, is 4, and T sub 1 is 2. Answer is 8. That's T sub 3. T sub 4, that would be T sub 4 minus 2 times T sub... Oh, I wrote that wrong. T sub 4 minus 1 is what that should be. Times T sub 4 minus 2. That's really T sub 3 times T sub 2. T sub 3 we just found to be 8, and T sub 2 is 4. 8 times 4 is 32. Sweet. So we've satisfied the directions. We have found T sub 3 and T sub 4. Your terms, 2, 4, 8, 32. Your ends, 1, 2, 3, 4. Is there a pattern? Is there a pattern? Let's see here. Multiply by 2, multiply by 2. Oh, but then you multiply by 4, so that doesn't work. The next term, just FYI, would be 256. You know what? There's no arithmetic pattern. There's no geometric pattern. This must be a neither. So how are you going to come up with an explicit definition? How are you going to come up with an explicit definition? Well, you know what, guys? I don't know the explicit definition. I have not been able to find a pattern for this one that works. 2 years ago, I had a couple students that finally found one, and I gave them some extra credit. So if you can find an explicit definition for this pattern right here, I will give you extra credit. It's a tough one. Good luck. Hope you have fun. Well, I believe that's all I'm going to do for part 1. I'll catch you later in part 2.